catch up to you guys. So the first one, hopefully, there's a lot of moving parts there, but it's a basic. It's the classic probability problem is put a bunch of poker chips in a bag, 4 red poker chips, 6 green. I'd rather have people in a haunted house, but it's the same exact problem, right? Put things in a thing and then pick something out. And, so what do I need to do very first thing? Yeah, I need to know what the total, so I know what all the denominators are. So what do I get? 18, 20, 27? Okay. 27 total. Please, dear God. Now, what I'll do on a quiz or a test, and this is where we're going to have that double quiz. Remember that on the homework sheet? So it's just going to be like chapter 3 is its own little thing. So I give it its own little double quiz, or what do they call it? Double quiz or mini test? Double quiz. Okay, good. Mini test freaks people out, so I just call it double quiz. That means it's about twice as long as a normal quiz and counts twice as much. It's crazy. If you make a mistake early and you miscount something, I'm not going to count every one of them wrong. I'm going to take points off for that one thing, right? I've had teachers that you make a mistake in part A and everything else is just shit, even though you did it all right. I'm like, what point does that make? So what is probably the person is a Democrat picking somebody at random? 7 out of 27, which is roughly what? 25.93? Because the thing is 925, right?
Yeah.
You gotta be careful now. You gotta round correctly. Just a little over a quarter, right? So it's probably the person that we randomly picked to save as a Republican. 11 out of 27, which is approximately 40.74. Spam. Now, please realize, I don't know if you really picked up on this. I think you should know by now how big I am about seeing work, because that's it. That's the thing I need to see. So this is your work. If you just put this down and you get it wrong, I'm taking all the points away because I have no idea what you did wrong. It might have been a little tiny mistake because you didn't show me anything. I don't know. So show me your work. That person is a communist or a Democrat. Yeah, I got 7. I got 10 things that match what I'm looking for. I like it out of 27 total. And whatever the hell that is. 37 point. Remember, Mark? 04. I was like, how do you write nurse marker? It's a percentage. That person is not an independent. Yeah, there's 2 independents, so the rest of them must be not independent. 25 out of 27, which is approximately 92.59? And of course, the one that was sort of tricky, but not really. That person is a member of the Green Party. They're in a different haunted house. 0 out of 27 people matched only for 0%. I like it. Alright, so how was that problem? That problem can take on a lot of different looks. It could be chips in a bag, people in a house, salamanders in a pond, whatever the hell. Right? Just things in a thing, and I'm going to pick something at random. Things in a thing, Jeff. It's very descriptive. Put the things in the thing and do some stuff. So, I'm pretty much always going to give you this kind of problem. This is what's called a contingency table. It is section 3.4 in the book. So what we're doing right now, in case you're curious about what section we're in chapter 3. Because all the ideas in chapter 3, they've broken it up in a certain way that I don't love. They're all so connected that I have to talk about them all at once. So today is going to be like the overview of everything, and then tomorrow. The next day we're going to do some little details in each section, and that'll be chapter 3 complete. So of course, what's the first thing I want to do when I see one of these bad boys? Add them all up. 9 is 2. And I got 15 50. So the 176, and then you double check. 165, 176. Cool. All right. So the problem, if I pick one person random, and these are always separate problems. This is not this, and then whoever's left is this. They don't build on each other. You see, that's another mistake I see people. So I pick one person was probably the 10 Grossmont. Yeah. 126 people, 10 Grossmont out of 176 people. What, do it again? 71? 59? Alright, cool. Is a business major. Yeah, 92, I like it. Out of 176, which is whatever the hell it is. What about, I heard the 0.27? 52? Okay. Alright, here's the first interesting one, right? Is a computer science major or attends Grossmont. So the way I would do this, well, what'd you guys get? How'd you do it? 137, exactly. It says, if you do all the Grossmont people, 126, but I still have to count these 11 computer science people. I haven't counted them yet. Exactly. Or you could always do 126 Grossmont, 73 computer science, minus the 62 people you counted twice. I mean, that's the formula. But you see how the formula is harder than it really had to be? Yeah. And it's not shitting on formulas, by the way. It's just, if I had the situation where I could count, of course that's going to be easier. Probabilities are all about counting. So if I can see everything, I can just count up what I need. But if I can't, dear God, the formulas are the only way to do it. Out of... I forgot. What is it? 77.84? Okay. I got you. 84, Jeff. Get a calculator, man. You got one, huh? Is a math... Now, here's the one that people always trip up. We are going to get a formula for and. Do you notice how we don't need it? We did an and problem earlier. We didn't need the formula. The formula is disgusting because it's a general formula that covers every possible situation that has the word and. And right now, you don't even know what that means because we've only seen this kind of situation here. This is a simple and. I've got everything I can count. What does this person have to do? They have to do two things. They must be a math major. They can't be any other major. And they must go to Cuyamaca. So, how many people do both things? 2. Only 2 people are math majors that also go to Cuyamaca. And is intersection. So, intersection of math with Cuyamaca is 2. Out of 176. I still don't know anything about the person, so it could be any of them. The only time the bottom changes is if I give you information about the person. Then it's less possible people, or less possible poker chips, or less possible salamanders, or whatever. And what's 2 out of 176? Whatever. Who? 1.14? Is that what you guys got? I got some. Okay. Some pained faces, but maybe just didn't like the number. Poor little number. Alright, so here, let's make sure we can read this correctly. In fact, what's the whole question? Each one of these A, B, C, D, they're not the whole question. What is the whole question? If somebody's selecting a random from the group below, find the probability that that person goes to Grossmont. The probability that they go to Grossmont, given they're a computer science major. So what do I know about the person? I don't have a clue if they go to Grossmont. We know that they're a computer science major. Find the probability that the person goes to Grossmont. If we knew they're going to Grossmont, it's 100%. Next. I don't know. The probability they go to Grossmont. Given that they're a computer science major, so I know they're a computer science major, so how many people am I talking about then? Careful. How many total people could it be? Yeah, so out of this, because there's 73 computer science majors. So whenever you have a given, the bottom will become related to what you're given. If I told you I had a red card out of a deck of cards, it's not all 52 cards, now it's 26 cards. I know some of you guys maybe don't know cards. But you know those red cards are black cards, right? So if I give you information, the bottom will get smaller most of the time because I can eliminate groups of other things. So it can't be a math major. It can't be even a screw that. So out of those 73 people, how many match what I'm looking for? 62 match the Grossman. 62 match what I'm looking for. Got it. And whatever that is. I don't know if you picked up on that. That's the answer. And then however else you want to write it. Great. Now one thing about this. Do we already have a question about the probability of going to Grossman up there? And so, real quick, this will help me on what I'm about to say. What do you guys get for 62 divided by 73? 84.93?
Yes.
Okay. Is there already a question about the probability of going to Grossman? Yes, A. You just have another little puberty there. Grossman. They just don't stop coming. It was almost 72%, right? Only 71.5%. So very cool with that. If I tell you, oh yeah, the person we picked was a computer science major, what happens to the probability that they attend Grossman? The probability they go to Grossman goes up. It changes. It gets higher. There's a higher chance. Now, let me let that sink in for a second. So this is sort of like the research they're doing to see, okay, if we can tell what kind of genes you got, maybe some of those genes will tell me if you have a propensity for a certain kind of cancer. So the probability you'll get a certain kind of cancer, given that you have this gene, is higher than it normally would be. Let me let all that sink in. You've all heard this stuff, right? The probability that you'll die early, given that you smoke, right, will go up than what it is normally. Do you understand? I'm not railing against you if you smoke. I'm just saying that's the fact, right? So what we call this is dependent events. The probability that somebody goes to Grossman depends on if they're a computer science major or not. Why does that make sense? Because if they're a computer science major, almost 85% chance. If I don't know what kind of major, only a 71.6% chance. So does that word dependent make sense? It depends on if there's a computer science major or not. Let me like that. I like the looks of you. Oh man, some of you guys look like you want to hurt me. I'm going to call for an escort to my car. Like, what did I do?
You said that and was intersection, so it's or.
Or, the other word for or is union.
Okay.
Yeah.
Oh.
Getting everybody together. Yeah. Of course, if you take a vote, you don't want to count anybody twice, and that goes along with the formula for or. I like it. I like it. Cool. Okay. So here's the last thing we'll do today. I'm gonna get out of here a little early so we can brave the roads. I'm going to want to create the formula for this, for the given. I'm going to show you the symbol. I can't remember this book. I know it sounds really funny for a teacher to be like, does this book use... But every book is different. I can't remember if this book uses my notation. Yay! They do. Okay. So in symbols, the way I would write this, because this is a huge requirement for you, is to be able to write an English situation in mathematical symbols. So the math symbols for this question would be the probability goes to Grossman. We normally give an event a single letter. It's like a variable, right? So capital letters are event variables. Is that cool to say though? Did you know? Again, some of you guys just look like you ate something horrible. Given. So this is the symbol for given. Unfortunately, it looks a little bit like a division symbol, but it's not really. The probability Grossman given computer science. I would probably do CS for computer science, just in case there's another C.
Can you put X if you're just normal? Does that do this?
You always want your letters to relate directly to the physical idea. So how would I write this in symbols?
Oh, no, I just mean like for a new, just a formula.
Oh yeah, we're going to do it in a second. I'll use A and B. A and B are like your X and Y variables for probability. How would I write this in symbols?
M.
Yeah, M. And
C.
yeah, see, that's why I want to use CS for computer science, right? So C could be Quimac. You guys with me? Probability of Menk. Menk. Alright. Stop. Alright, I'll stop. So let's look at this one specifically. What does that 73 relate to?
Computer science.
Computer science. It kind of makes sense. Given computer science, so the bottom is now going to be related to computer science. It could be the number of people that are computer science majors, because that's what I know about the person. Now here's where it gets interesting. What's that 62? It's not Grossmont students.
Computer science.
That's Grossmont students,
For computer science.
not or. Those 62 people, what do they do? Those 62 people, what's special about them?
Here's at first one.
True. So what's the probability word that's hidden because of the English? They go to Grossmont and they're computer science majors. Let me stop right there. So if you know they're a computer science major, what's the only way they could also go to Grossmont is if they do both. If they're a business major goes to Grossmont, that's not going to be there. So here's the formula for this specific one, and then I'll write the one in general. This formula for this is probability Grossmont and computer science divided by probability of computer science. That's what we actually did here, believe it or not. You guys are all like, I don't believe it, Jeff. That's bullshit. Well, let's take a second. I'm sure somebody out there is thinking that. This is all bullshit, Jeff. All right, somebody help me out. Now, let me give myself some more room. What is the probability Grossmont and computer science? Let's see if this is true. See if I'm full of shit or not.
62.
62 out of 176. What is the probability of computer science major by itself? Probably computer science major. 73 out of. I know a lot of you guys don't like fractions, and now that's a fraction inside of a fraction, right? That's what I call fractception. What do you guys know what happens to divided by 176? They just freaking cancel. So you get 62 out of 73, which is what we got without the stupid formula, right? Again, I just say stupid formula because that's stupid to use it right now, but this formula is necessary. So here is what it is in general. The probability of A given B is the probability of A and B divided by the probability of B. So let me see if you can help me out. What is it the other way around then? What's probably B given A? We'll let you guys write that down and then think about what that is. What's the difference? Yeah, this can, you could start to put together a formula sheet if you want to. This will be on your formula sheet for the little double quiz. What would this one be then? What's probably B given A using this form here?
The probability of A and B over probability of A.
Yeah. Now you did one thing that I want to make sure everybody understands. A and B versus B and A, they're the same damn thing, right? If I'm like you and you, come with me. Which one you want to go for? No, just come with me, both of you. Shit. So A and B is the same as B and A. Are you guys with me? What's always on the bottom of a given is what's freaking given, right? Let that make sense. That's what I know happens. So it can only be out of those things. I like that. All right. I don't want to do this too often, but I think that's why not? That's plenty for today. You got your test back. So you guys got to go look at your rulers. You got to come to see me if you need help with the corrections. Ryan, get out there. Go slowly on the road. Oh, thank you. Sure.